We welcome you all to the second webinar under the technical exhibition of MindSpark'21, one of India's most coveted technical festivals. Taking the legacy forward, this year too we're having a webinar series as a part of technical exhibition, and we hope to conduct a successful technical exhibition 5.0.
We hope all of you are doing well in these difficult times. The pandemic has affected all our lives in almost every aspect. We believe that every difficult situation is an opportunity for innovation, and here at MindSpark, we strive for the very same.
On this warm note, we are thrilled to welcome you all to the second webinar of Tech Expo webinar series of the 15th edition of MindSpark.
We deem it as an honor to have INO at Technical Exhibition 5.0's webinar series this year. We all are fascinated by neutrinos. These superabundant, almost massless particles can reveal countless secrets of our universe. And guess what? We have one such research facility in India whose aim is to study these interesting particles. The India-based Neutrino Observatory INO project is a multi-institutional effort aimed at building a world-class underground laboratory with a rock cover of approx 1200 meters for non-accelerated based high energy and nuclear physics research in India.
With great honor, we would like to welcome our speaker for today, Dr. B. Satyanarayana. Dr. B. Satyanarayana sir is currently working as the project coordinator in INO, India-based in Neutrino Observatory. He is a visiting professor of American College of Madurai, distinguished visiting professor at Symbiosis Institute of Technology, Pune. His area of research interest includes detectors and instrumentation of high energy and nuclear physics experiments. He is a BTech in EMTC from Jawaharlal Nehru Technical University in Hyderabad. He also has a PhD in physics from IIT Bombay. He has authored like around 250 research papers which are published in national as well as international journals. With such a personality among us, no doubt that this session is going to be very interesting and informative.
Now I request our speaker to take on the virtual dais and proceed with the webinar. Over to you, sir.
Thank you. Can you see my slides?
Yes, sir.
Okay. Also, can you confirm if they are moving?
Yes, sir.
Okay, excellent. So thanks, Harsh, and also Shruti for your wonderful introduction. I was happy to kind of hear quite nice words about the neutrinos and INO project. I must also sincerely thank Srishti, who in the first place invited me to give this particular talk. I'm very honored indeed to talk to you and your friends. I was told that I have about half an hour time for my presentation and about another 15 minutes for question answers. I hope you will be able to kind of interact well with me after this half an hour. I must say that I kind of prepared a slightly longish presentation, so therefore I'll be skipping quite a few in the process. Please don't get disturbed by the slides that I'm skipping. So as mentioned by Harsh, the India-based Neutrino Observatory project is a very prestigious, in fact, one of the nation's mega science project. And he also mentioned nicely about the importance of neutrino. Maybe I'll say a few more words a little later. I'm actually, honestly speaking, don't know much about the composition of today's audience, but I guess there are enough audience coming from electronics and telecommunications or computer science and such branches. So I tried to kind of a little bit give an emphasis on sensors and instrumentation and how important they are for experimental science applications like the INO project itself. Incidentally, the one that you're seeing on the screen, basically a barren mountain, is where the experiment is supposed to come up at some point of time. We plan to kind of dig a tunnel from approximately from where I have the pointer, and then about 2-kilometer tunnel is going to be dug inside and approximately coming below this peak of the mountain, and inside which we plan to build this massive experiment. Some details probably will be known as we move along, right? Neutrinos, yes, I mean, as I think Harsh mentioned, is a very Very, very interesting particle. This was proposed by Wolfram Pauli in 1930 to explain what it's called beta decay. I tried to keep the science part a little on the low key, just thinking that maybe not all of you kind of studied science. But what it actually says is that, if you look at this little simple equations, a neutron going into a proton plus electron plus this neutrino, anti-neutrino rather, and a proton going into neutrino plus so-called positron plus neutrino. And remember, in 1930, people didn't know this third particle, right? Okay, so when they kind of tried to measure the energy of these either electron or positron, which should have been a fixed energy like what you will see like a delta function here, people actually saw the beta particle is same as electron or positron particle. One has actually seen a continuously varying energy, which is was very much puzzling because we should have actually had an electron coming with electron or positron, doesn't matter, coming at a fixed energy, right? So much so because that time people didn't know what neutrino exists. So it was like a big surprise, and many people felt the law of conservation was actually missing here. And people like Niels Bohr said that maybe there is something wrong with law of conservation of energy and so on and so forth. Okay, the fact was that Pauli explained saying that, look, I mean, it is not just the two body here, but there is also third particle, which is actually part of this equation. Now, if you have the third particle here, the energy is distributed between a beta particle and the neutrino. And neutrino, of course, is a very, very tiny particle and nobody could detect it. So therefore, part of the energy is being taken by neutrino. And how much energy that neutrino is taking for every reaction, that why this particular varying energy was coming up. So this puzzle was solved by him, but later on an Italian scientist by name Enrico Fermi, a couple of years later, actually put in the so-called the theory for this beta decay, and then everything was kind of somewhat better understood. But 1930s to 1954, the neutrino was remained as a theoretical under the theoretical framework in some sense. And in fact, Pauli, who, as I said, proposed this particle, was kind of so sure that there's such a tiny particle almost went missing for detection. He was quite sure that it cannot be detected. So when these two gentlemen, Frederick Reines and Clyde Cowan, when they wanted to set up an experiment to actually discover or measure the neutrino, for that proposal, apparently, Pauli has sent a telegram to the funding agency saying that, look, I mean, it is very difficult for this particle to be detected. Please don't waste any fund, under this experiment. Luckily, the telegram did not reach, and the government has actually given funding, and the rest was history because in 1954, both these gentlemen actually discovered neutrino by actually an anti-neutrino by setting up an experiment like this. Okay. So this was in 1954. It actually took 25 years, to kind of make a theoretical framework into a reality. Now, neutrinos are all over the world, all over the universe, and there are large number of resources that you can think of. Big Bang is one of them, which happened almost 14 billion years ago, and we'll see a little soon in the next slide, the neutrinos which are produced there are still around us, and what you call relic neutrinos. Supernovae is another source when massive stars collapse and gigantic kind of explosions happen, and just before that, the huge flux of neutrinos kind of come out before the light signal actually gets emanated. In some sense, neutrinos act as an early warning signal for supernovae to be observed by optical telescopes. Sun is a big source of neutrinos by what is called thermonuclear reaction, where that is how, in fact, the energy in sun is produced. Four protons combining, fusing into an alpha particle, producing two, let us say, positrons and two electron-type neutrinos, and 25 MeV of energy at every time. They're also produced in cosmic rays. The way it is produced, the cosmic ray particles which are coming from outside the atmosphere, they actually interact with the molecules of, let us say, atmosphere and produce very short-lived particles called pions. Now, pions can be charged pions or neutral pions, it doesn't matter, but they very quickly decay into, let us say, muons and so-called atmospheric neutrinos. You see, here we are writing electron-type neutrinos, here we are typing muon-type neutrinos. The muon itself very quickly decay into a positron and an muon neutrino, and this electron type neutrino, and then one more muon type neutrino. So you can really see this like a cascade of particles coming from cosmic particles and producing large number of electromagnetic shower. So on the surface where we are all sitting, there is a huge flux of neutrinos along with muons themselves are hitting us. These are natural in some sense. All of these are natural source. Of course, neutrinos are also produced in the by people in the nuclear reactors. And in fact, as I said, neutrino was actually discovered in one of the such nuclear reactor experiment. And particle accelerators, which accelerate particles and make them head-on collide with each other and producing particles like what you have one at CERN and so on. They also produce neutrinos. So, right, these are, you can call them nuclear reactors and particle accelerators like man-made, and cosmic and sun and Big Bang and supernovae are natural sources of neutrinos, right? Okay, neutrinos are very, very unique. I mean, I keep saying this word many times probably. They are the most abundant particles after the photons, which are roughly about 400 at every cc cubic centimeter of space that you see around, and neutrinos are around 300 per cc. They're very, very light. We told already many times, they're much lighter than electrons, maybe 1,000,000 times. And they're invisible, of course, because they don't interact with light. You cannot stop them easily, just like the way you do for alpha, beta, gamma radiation. And trillions and hundreds of trillions of neutrinos from sun and other sources, which I just now mentioned to you, are actually passing through every second as we are speaking. And very interestingly, since we said that thermonuclear reaction in sun actually produces neutrinos, there is a way of saying that, if there are no neutrinos, sun will not be able to shine. And if sun doesn't shine, then you and me do not exist on this earth, isn't it? Because that's a very interesting kind of aside of neutrinos. Okay. Yeah, I mentioned to you, I mean, at Big Bang, and you can actually see at a scale of 10 power minus 43 seconds, in fact, the neutrinos are the only particles that exist at that point of time and temperature and so on and so forth. And since the neutrinos, as I said, they interact very, very rarely, okay, they should have been able to kind of move around very, very freely from that sea of matter long even before the light could have actually, passed out. Perhaps maybe within 1 second, less than 1 second of a Big Bang, right? In fact, it took almost about 400 million years for the light to kind of come out, but much, much, much before that, neutrinos were released because they don't interact with any other material, and they remained there just because they don't interact. And then many of the neutrinos which are produced there, they are actually going around because they just move around without interacting with any of the matter around even now. Okay. In fact, that is one way, maybe that is telling you something about what is the earliest insight into our history. If you really want to know what is that something happened so much closer to the Big Bang, I think neutrinos could be one kind of signal. Whereas while studying Big Bang using other materials, we were more or less somewhere half the scale. We have not even reached more than half the scale of the 14 billion years ago. So you can really see that neutrinos have fantastic ramifications of knowing, understanding cosmology, understanding particle physics, understanding many, many other things, right? As I mentioned before, when neutrinos are produced in the sun, it actually takes, I just mentioned to you, tens of millions of years to leak out from the center of the sun. Okay, but then it only tells about what is the condition that happens on the outer region of the sun. But neutrinos are produced deep inside and passing through the entire kind of Earth in less than, maybe one chance of 1,000 billions being stopped by terrestrial matter, right? And you should also remember neutrinos are not part of the atom that we studied, right? We studied, atom has a nucleus and electrons around. Nucleus has so-called nucleons, protons and neutrons and so on. And of course, protons and neutrons are made of quarks and so on. We didn't learn about neutrinos being part of the atom, right? But they are created through many processes. One you just now saw, so-called beta decay, and then they're all over the world at large numbers. And as I said, they're flying everywhere at the speed of light, okay? And something interesting, right? I mean, typically a neutrino has to zip through 100 billion people before doing anything to a person. That means if you make people to stand 100 billion people in a straight line, that probably one neutrino will actually interact with one of the person. Just like I said, without neutrinos, sun doesn't shine. There is something very interesting anecdote here, that our body itself comprise of about few tens of milligrams of potassium-40, which is a radioactive beta radioactive source. That means we are emitting continuously about few hundred million neutrinos every day. And as we are releasing them, as we are producing them, they just fly out, right? They just keep going because, as I said, they are hardly stopped by any matter. That means all of us produce our signatures in terms of neutrinos, which are very specific to our own bodies. So this is the experiment I mentioned some time ago. Rhinus and Cohen sitting there, set up in one of the nuclear reactor, producing a large number of neutrinos, rather anti-neutrinos are produced. And what they have made a very simple setup here is basically a big tank of water with the scintillator plus cadmium chloride. Okay, about couple of 100 liters of water and about 40 kg of cadmium chloride. Now, the detector, as you see, the circular objects are those so-called photomultiplier tubes, which actually pick up the light, tiniest light that is produced by any interactions. From the nuclear reactor, a large number of neutrinos come in. Okay, and when they come in, they have, of course, once in a while interact with the body, with the water that you have put in, and then produce what is through inverse beta decay. They produce so-called positrons and neutrons. Okay, now these positrons will again interact with the electron, which is part of the water, and produce two gammas. They annihilate with each other and produce two gammas, which go back to back, one gamma this side and one gamma this side. But the neutron that is produced will actually go through multiple paths. It's something like a slow reaction here, and they actually what they call it is captured by cadmium, which is part of cadmium chloride, and then produce something stable, 108 cadmium becomes 109 cadmium, which is a stable one, which will quickly decay and then produce 109 stable cadmium with a gamma here. Now, what is the game? The game is that you first look for these two gammas, which are going back to back here. And after some time, maybe a few microseconds, you look for a gamma that is produced separately. Both of these as well as this is actually picked up by the photomultiplier tubes. Okay, and that is how you can confirm this plus delayed gamma is an interaction for actually neutrino interaction. And you can believe even those days with such a simple equipment, their predicted measurements matched quite well with the predictions and so on. So that is how these gentlemen were the discoverers in some sense of the particle. Way back in India in 1965, my seniors in Tata Institute of Fundamental Research, working at Kolat Goldfields, at about 2.3 kilometers underground, setting up a very, very simple such experiments using so-called scintillation detectors, which produces light on passage of particles, and then those light that is produced by the particles as they pass through what are called neon flash tubes. These are very thin tube-like structures. They actually produce these the light when a charged particle intercepts them. Okay, so using those stacks of vertical stacks of this the detectors, they were able to kind of detect neutrinos which are produced in the Earth atmosphere. One of them, which I mentioned to you, the so-called cosmic ray atmospheric cosmic ray neutrinos, which are produced in the Earth atmosphere. Okay, and so this was the first discovery in 1965. In fact, incidentally, the paper was published on August 15, 1965. So we are pioneers in the atmospheric neutrino physics. Okay, now where does neutrinos stand in the so-called standard model of particle physics? Some of you must have kind of seen this. All that what we know about the universe today, we know, and if you can kind of tabulate them just like the way you do for a let us say periodic table in chemistry, right? There are fermions, there are particles here, and there are gluons, the ones that mitigate the interactions between these particles. Further, fermions are divided into so-called quarks, right? And sometime back I was telling about, for example, protons are produced, comprised of 2 up quarks and 1 down quark, and neutrons are comprised of 2 down quark and 1 up quark. There are also 4 other quarks. Incidentally, I was also part of the discovery of a top quark in Fermilab in 1995, which was one of the heaviest quark at that moment of time. And on the leptons, you have 3 particles, at least one of them I'm sure you know, which is an electron. Just now we talked about. And there is also another particle we mentioned just now, which is produced in the Earth atmosphere. It's about 200 times heavier than electron. And even another heavier electron, you can say electron-like particle, which is tau. Now, below them, you can actually see 3 of these particles. These are all 3 are neutrinos, and one corresponds to each of these particles. So you have so-called electron neutrino, muon neutrino, tau neutrino, right? And so this is of course, a part of today's presentation. But these are how all the particles that we know today are actually tabulated. And they're, as I said, they're mitigated by the force carriers here. Of course, the strong interactions that happen inside the nucleus are mitigated by so-called gluon, electromagnetic interactions by photon, and the Z and W actually mitigate the interactions, so-called weak interactions that happen for particles which are leptons. And you, I'm sure, remember sometime back, 2012 July, we also discovered another brand new particle called Higgs boson, which incidentally I was also part of this particular experiment. And this was the latest discovery in terms of the gauge bosons, right? And so after this, neutrinos are at the center stage because that has, as I said, many ramifications for many fields of physics. In fact, one of the very earliest part of the problem was, since there are 3 neutrinos here, okay, and somebody by name Ray Davis tried to kind of look for neutrinos which are produced in the sun, called solar neutrinos or electron type neutrinos. He actually set up a huge experiment comprising of a chlorine type kind of a solution. So the neutrino interacting with chlorine 37 is supposed to produce argon 37 plus an electron. Now this person was actually set up few, thousands of liters of such a chlorine liquid, and then he's a chemist, by the way. And then after doing an experiment, you typically take this entire thing into counting in an experiment very painstakingly to see how many argons are produced, and you would say, okay, so that means there are so many neutrinos came and interacted with my detector. But unfortunately, he found that the number of neutrinos that he detected are only a third of what his friend by name Bechdel has actually predicted that so many neutrinos produced in the sun. That was, by the so-called standard solar model, which I already mentioned to you some time back. So that was a big puzzle. And then people did not believe that his experiment was of any use because he's not able to detect the number of neutrinos that are produced. But it was a big surprise later, another very big experiment called Super Kamiokande. You can see that this is about 50 kilotons of water, put it in a big tank, and which is actually seen by thousands of photomultipliers. And incidentally, the picture that you see are the people who are going on a boat and trying to kind of maintain this detector. And of course, it takes a long time for me to kind of explain, but the main thing to kind of tell you is they also discovered that only about a third of neutrinos which are produced in the sun were able to get detected. And later in Canada, by name Sudbury Neutrino Observatory, has actually set this problem for sure by saying that, look, I mean, there are these three type of neutrinos, and then as the neutrinos travel from sun to the ground, they actually oscillate. They kind of move they change their flavor from electron type to neutrino, muon type, and muon type to tau type, and so on. And that's why, since this experiment by Davis or the experiment by Kamiokande, only sensitive to solar type of neutrinos, electron type of neutrinos, therefore, they are not sensitive to other two types. So therefore, they were only seeing a third of the neutrinos that are produced, whereas Snow experiment is sensitive to all three types of neutrinos. So they were able to kind of detect all three of them together. And that is how the solar neutrino puzzle was kind of solved. And that was an important discovery somewhere in mid-90s. Okay. And so therefore, starting from Frederick Reines and Cohen, unfortunately, he passed away by that time. But for a discovery that happened in 1954, they won the Nobel Prize in 95. And 2002, Ray Davis and Toshiba for the Super Kamiokande experiment that I mentioned to you, they won the Nobel Prize. And only about 5-6 years ago, Arthur McDonald and the Snow experiment that I talked to you about, and Kajita, also from Super Kamiokande, actually won the third Nobel Prize for the neutrino oscillation. So Kamiokande experiment was very important. It won 2 Nobel Prizes for neutrinos. That is a very, very important milestone in the neutrino field. Coming to the INO project, this is, of course, obviously for neutrino physics. There's a big collaboration of about 25 groups of IITs, DA institutions, and universities. And this is the kind of money that was sanctioned. And the project includes construction of an underground lab, construction of a massive detector like the way you saw for the Kamiokande experiment, and also setting up a center for high energy physics. Okay? But what is important for you, I would say, is also INO runs a so-called graduate training program, a PhD program under the HBNI, Homi Bhabha National Institute, where students working on neutrino physics and the other fields, they get their PhD. So this is the INO collaboration, which was spread all over the country. About 100 scientists worked on this experiment. This experiment should be coming up somewhere between Madurai, about 100 kilometers west of Madurai, between Kerala and Tamil Nadu border, somewhere precisely at this place, right? So that is the location. The land for this was given gratis, free of charge by the Tamil Nadu government. As I mentioned to you in the very first slide, there is going to be a tunnel that is prepared. Go inside, and then this is about 2 kilometers long. And once you reach inside, at the end of 2 kilometers, you would actually have a huge tunnel about 130 meter long by 30 by 30 meter wide. Is going to be constructed along with few other tunnels for other experiments, few other caverns, laboratories for other experiments. And this picture here is where the massive INO experiment is going to come up. This is the proposed site and some facilities there. And the center where we want to build Center for High Energy Physics right now, of course, is still a barren land, but we hope to kind of build a prototype detector there very soon. Okay, this I kind of already mentioned, so let me kind of skip. So this detector that we plan to build is something like, looks like this. This entire mass that you see is made of iron, where the nucleons, which are part of the iron, are the kind of source for the neutrinos to come and interact with. You will also see these, purple colored kind of strips here. These are the magnet coils. These are copper coils through which you flow very, very strong electric current, and which will magnetize the like a regular electromagnet. So the entire detector, which is weighing about 50,000 tons, is going to be magnetized to a field of about 1.5 Tesla. And they will help you to kind of measure the energy of the particles which are coming out of these interactions. Now, there are sensitive detectors called resistive plate chambers, which we'll describe very soon. They are going to be used to be able to observe record these particles which are kind of produced. So we are going to kind of use about 30,000 such sensitive detectors, which if you cover on the ground, they will be about 100,000 meters square. This is a very massive kind of detector. The signals are read out by about 4 million detector channels. So the signals that are produced in the ICAL, iron calorimeter detector, is coming through literally 4 million wires where you need to record the entire data. Okay, so this is what I mentioned to you some time back about the cosmic ray muons. So the cosmic particle coming and producing pions decaying very quickly into muons, and muons further producing the neutrinos. And you can get a picture of how this is. This is roughly a kind of balloon flights that we have. This is around 30 kilometers, and this is the Mount Everest, and this is where we are on the ground here. And the way this particular detector is made is by very, very heavy, very, very massive kind of iron plates, which are about 4 meter wide and 2 meter long and 4 meter wide iron plates, which are stacked one above the other, each weighing about 4 tons. And then there is a gap that is maintained between each of these plates, and 150 such layers are actually stacked together. And the gap that are maintained between the iron plates is into where you kind of insert the sensitive detectors later. Okay, so this is the construction that is made of. Just one slide, I want to kind of show how beautiful this concept is here. If you think this is the Earth, and then you build one like like detector here, the neutrinos which are produced in the Earth atmosphere above, they are going to come up from the top and reach your detector. But remember, the neutrinos which are produced on the other side of the Earth also can come through all the way and then can be detected from the bottom to the top of the detector. What is the difference? Here it is only about 10 to 30 kilometers distance. Here it is something like thousands of kilometers distance. So you will be able to kind of, with using one single detector, you can detect particles which are coming from the top, which are also coming from the other directions. And using that distance information, you will be able to kind of study the neutrino oscillations, which I mentioned to you earlier. Normally, experiments elsewhere, they use two different detectors, one to detect the short baseline they call, and one to detect the long baseline. But here you have an advantage of actually having one single detector to be able to kind of do both of these functions. Okay, so using this, we also try to, one of the important problems that we want to attempt is what is called matter effect and the neutrino mass hierarchy. What is that? The neutrinos that I showed you consisting of 3 types, they are called flavor types. Both of them are made of so-called masses, which are nu1, nu2, nu3. Right? We know that nu1 is smaller than nu2, or nu2 is higher than nu1. But as of now, we don't know the mass nu3 is higher than these 2 guys or lower than these 3. So either it is 1, 2, 3 or 3, 1, 2. So one is called normal hierarchy. The other one is called, let us say, inverted hierarchy. This is still a problem which is not solved. Using experiments like INO, we'll be able to kind of tackle such kind of problems. So it's very important. Just I will quickly kind of try to show. Just a minute. Oops. Yeah, how by a brief, very small animation, how the detector is going to be constructed. So this is the long 2 kilometer long tunnel on which the iron plates are actually being shipped by a truck. And these iron plates are going to kind of be stacked on this particular area, which has already been prepared by using concrete blocks. And then, layer by layer, iron plates are going to be picked up from the truck and going to be stacked one above the other, right? Okay, and okay, I think I'm not sure I have enough time to show this picture, but let me at least show you until it kind of, yeah. So, okay, so then there are also these magnetic coils that I mentioned to you, which are also going to be embedded in between. And then, one layer at a time, they're going to be stacked. And you will see very soon 150 such layers are kind of formed. And similarly, you will find 3 other modules are going to be formed and so on. Okay. So I think I'll try to skip. So the detector, the so-called RPC detector is a very simple to make. It is made of 2 glass plates. We call them electrodes, and they are kind of made parallel to each other. And the very sensitive gas, which is comprised of 3 gas mixtures, actually flow through this. Now, on the outer side of the glasses, we paint with some graphite and apply about 10 kilovolts field, which is actually used for the particles when they pass through. Okay, the neutrinos coming in, let us say interacting with the iron nucleons, and then when the particles like charged particles that are produced, they pass through this gas, ionize, and produce the signals, which are actually picked up on X side as well as Y side, like a cross wire, and you will be able to get, like a coordinate of the particle, the track as they pass through. Since there are 150 such layers, you will be able to kind of look at how those things are passing through, how the particle is actually moving from one layer to the next layer. So you can actually see the good part about such a detector is they're actually made of very simple materials. These are like buttons which are used to hold these 2 glasses together. This is the nozzle through which gas is flown, and these are the spacer to which you actually put, the sealed entire detector. And the signal comes through such kind of pickup panels, which are made of, plastic and copper strips, like what you can actually see. So when you make such a detector, it looks something like this. It is a 2 meter by 2 meter body, which you insert into the detector where there are such caps here. Okay, the signals which will come from such a detector or sensor are very, very nice, very beautiful, very sharp, and very fast signals, which are actually the ones that you need to prototype them or make them electronics about. After you make such a detector, we work to kind of test and see that everything is working fine by setting up what we call prototype detectors. And of course, they work beautifully, and that gives us satisfaction that we can really make large number of such detector in the industry, and they're going to work for the INO project and so on and so forth. Okay, so tracks like this, which are passing through, these are the cosmic ray particles, which are all going through all around. And when they pass through layers and layers, there are 12 layers of RPCs here. And you can see that they are leaving a nice track passing through them. And they will tell you that your detector is working beautifully. And if you decide one of such detector and whole night you work around with all those cosmic ray particles passing through, you can actually make like an X-ray of an RPC or a tomography of an RPC. And that is really telling you that these detectors are very sensitive to any charged particle which you need to detect in the INO experiments. And since the entire detector works with gas, so we also develop our own gas systems by which 3 different gas mixtures are mixed to a fixed proportion and they flow through these detectors. About 200,000 liters of gas flow through these detectors all the time. Coming to the electronics, the way we do it is starting from the RPC detector. The very tiny signals that you saw before are actually amplified and discriminated or compared. And then here, these blue boxes here are the so-called field programmable gate arrays, in which a lot of such logic is fused to do varieties of data acquisition needs. The sensor signals are very small. You need to condition them and then acquire the signals to detect and say that these signals look like what are produced by neutrino interactions. Okay, it also consists of very, very sensitive elements like time to digital converters, temperature, pressure, humidity monitors, MCUs, which are basically microcontroller units, trigger system, waveform generators, and so on and so forth. And the entire data comes through a network of switches, just like what happens in a typical corporate office. Now, when you require to process the signals coming from the sensors, you need to make your own electronics because these electronics are not readily available in the market. PhD students sit down and actually design such an amplifier or comparators or the front-end circuits, and then they go to kind of a foundry. A foundry is where the chips which you design gets kind of manufactured, and these ICs are called application-specific integrated circuits. A large number of such ASICs are actually produced by our graduate students, and when the chips are produced, they are actually put into regular printed circuit boards. those are kind of used. A large number of ASIC chips, both for analog as well as digital, are produced by the INO project as a part of this. I told you about the time to digital converter, which converts very precise time. It's like a stopwatch, like, if I want to measure from a start and stop, but with a resolution of 100 picoseconds, 125 picoseconds, very, very tiny signals. You might ask, why do you need to use this? You remember I told you the neutrinos can come from top to bottom, or neutrinos can go from bottom to top. How do you distinguish? Because they go at speed of light, right? Now, if I want to put a timestamp on these particles, whether they're going from bottom or top, I should be able to have it like a stopwatch, not of milliseconds or seconds, but of the order of picoseconds. Once again, students from IIT Madras who are part of this INO project actually designed such a ASIC circuit, which becomes a part of our INO electronics. Okay, so if you remember, I was telling you field programmable gate arrays are the main, you can say, workhorses for all the electronic circuits that we build around. And when you build them, you also require to kind of program what you call the soft core processor, which is part of the FPGA chip, to do varieties of functions and interface to the various devices. When you make all that put together, you make such kind of very, very high density circuit boards. And very funnily enough, the shape is not even a proper square, but more like a triangle, because you would like to put a lot of logic inside, but don't use too much of space, because most of the space you want to make it for a very sensitive device. 128 such channels coming from an RPC detector are processed using a TDC and an FPGA chip. The data that is digitized goes through a so-called Ethernet controller, Ethernet chip, and then comes up on your RJ45 connector. So therefore, you can actually build each one such detector as an IP host with an IP number, and sitting anywhere in the world, you will be able to kind of control these detectors somewhere in Madurai. So this is the main concept. So this is how the boards that are made look like, and the detector that is comprised of looks like about a 2 meter by 2 meter device. This is that board that you saw. The high voltage that is required to power up this circuit is also made at home, and all these front-end chips are mounted for Y side and X side in this part. That is what pick up these kind of circuits. So we make large number of, literally dozens and dozens of types of boards, and thousands of such boards are needed for electronics to make it. The trigger system, which keeps looking at the detector all the time to see whether the thing that is happening of our interest or not, is a very, very important system of such detector. This is again made by one of the PhD student for the INO detector, right? So it actually looks at patterns like this, the patterns of those hits, and then decide whether this event could be of a neutrino interaction or something gem, right? So, and it requires, of course, considerable hardware development like this. And then ultimately, when the data, as the detector is working autonomously without any intervention of persons, and when the trigger system signals that there is something interesting happen, the data from 30,000 such detectors come to the backend, which is a data concentrator, and you can see all this data comes in, and the timestamp that is provided by the trigger system is used to kind of compare and contrast the data, and ultimately putting a timestamp and putting the data into a server and so on. So that is the entire system. As I told you, even the high voltage systems are not something purchased, but they're actually made in-house and so on. And the detector systems that we built are produced nowadays in the glass factories in Chennai and Bombay, and they are now industrially kind of produced. And a lot of automation also happens in terms of in terms of paint, what I told you, the graphite that you want to coat on this for applying high voltage, and all such systems are actually automatized, so that you will be able to kind of produce these detectors on the in the industry, because you can't really make them manually. For example, this is a robotic machine which makes, so starting from a glass, putting those tiny buttons, putting the glue, all that entire operations are completely automatized. This is a glass company in Chennai, which is actually making these detectors. And even the prototype detectors in various operation was all being done by specialized engineers, and entire process gets automation. The magnetic field that is required to bend the muons that are produced is also kind of studied, and the magnetic field is measured in situ. Most of this work, if you really look at, for example, this is our lab in Madurai, and you can see large number of summer students, winter students, and graduate students. They actually participate in building the detector, install and commissioning this kind of detector. So this is one such a very tiny, about 4 meter by 4 meter detector. But importance of such a detector is it uses the same electronics, same detector, same copper coils, magnetic field, everything as it is supposed to be using for the final detector. Now, when you produce those kind of tracks, as you saw, one of the important tasks, of course, is able to kind of connect up those dots and see whether they make sense to what you expect, right? Of course, it's very easy to kind of connect up if the tracks are in straight line, but if the tracks are bent in a magnetic field, it requires special techniques. For example, sometimes we use neural network techniques, for example, to be able to detect or track such kind of tracks, even with the presence of very, very high amounts of noise, for example. I mean, if they are very, very clean tracks, it's very easy to do track fitting. But if it is in the presence of a big noisy signals, then you're required to kind of make learning systems. And one of the best learning systems, of course, is neural network, right? And sometimes we also use what is called Kalman filters technique in order to be able to connect up tracks from one point to another point. It works with prediction of certain coordinates and make certain measurement, and then measure the difference between what you predict and what you actually observed. And the difference between them, if it is large, then you need to go to one more iteration and then again predict with an estimate of what is the error and so on. So this process becomes very iterative, but this is very important method when you cannot very easily determine the tracks of these particles. And when you do such all these techniques, you will be able to kind of make such a tracks display, and then it will really tell you that due to magnetic field, the charged particles do bend, and you can actually see these tracks, basically saying that your detector is working very beautifully. I started this R&D way back in 2001, almost 20 years ago. But today we have large number of such RPC development labs in the country, and a lot of students are actually working on these detectors. So I just want to kind of give you a feel for what is happening today on this project. All the development work, characterization, the building detectors, building electronics, the magnet, the entire baseline detector is all ready. And all the detector components which are required for cosmic muon veto detector is getting prepared at this moment. And the construction of that center, which I told you in Madurai, we hope to start kind of very soon. INO is therefore very, very exciting mega science project. It's being planned on an unprecedented scale and budget. And ICAL, as well as other experiments, are, of course, produce very, very competitive physics, especially neutrino physics. But beyond that, INO is also an invaluable facility for many future experiments. I did not have time to kind of talk about all of their experiments, but more importantly, it provides a wonderful opportunity for science and engineering students to work on various fields like either detectors, instrumentation, physics, software, magnet, and so on. And the detector and instrumentation R&D, and as I told you that we also run our own graduate students program, these are the main thrust areas. It offers fantastic opportunities, as I told you, and challenges, of course. But again, I didn't have much time to discuss, but the same detectors that are used for detecting, let's say, cosmic neutrinos could also be used for the spin-offs in industrial and medical applications and so on. So with that, I'm sorry I had to really rush through because I didn't have much time, but thanks very much for your attention. And I'll be happy to take if you have any questions.
Yeah. Thank you so much, sir, for this session. It was really interesting. We have some questions from the live chat now. Also, like if someone has any questions, please feel free to ask them through the chat box. Um, so, sir, the first question is, are neutrinos involved or responsible for the bit flips that happen in computers due to cosmic rays?
Yeah, it's an interesting question. At some stage, I mean, of course, neutrinos are chargeless particles, right? So they don't really interact much with any material, including your silicon or other materials. So therefore, I don't say that they are responsible. But the same question also has cosmic particles. Cosmic particles has huge amount of charged particles. I mentioned to you, cosmic muons are one of them, which are slightly heavier electrons. So depending on what is called the flux is the, now let us say the number of muons passing through per unit, let us say cross section area per time, and they can cause, if the flux of these particles is very, very high, they can really damage the, let us say the transistor junctions, which can actually invert some of the logic that happens in the integrated chips, and they can create problems of so-called bit flips, about which the question was asked. And this is same as subjecting the chips under heavy radiation in nuclear reactors and so on, for example, right? This is what is called radiation tolerant. So whether your electronics can tolerate such kind of heavy radiation or not. So there are, of course, techniques to mitigate such kind of problems. But yes, cosmic rays in the very high altitude where the flux is high would actually have some effects on the so-called bit flips, but not neutrino.
Okay, sir. So now the second question is, can photons turn into neutrinos similar to pair production of electrons and positrons?
No. So the reaction that I mentioned to you in the early on, when during the neutrino discovery experiment, these are two electron. I mean, you can say they both are electron. One is positively charged, the other one is negatively charged, positron and electrons. They annihilate and produce protons, photons, okay, which are kind of is a carriers of light, which can be kind of detected. Neutrinos are produced by completely a different interaction, as I told you. One of the main interaction that I mentioned to you is so-called beta decay, which is nothing to do with photons. And the other one I told you is a thermonuclear reaction, which mostly happens in the sun. And also the third one I mentioned to you is about the atmospheric neutrinos, which happens as the pions decay into muons and muons decay into neutrinos. So there is no connection that way between these two.
Okay, sir. And next question is, how do we differentiate between neutrinos and anti-neutrinos in the detector, since both of them are electromagnetically neutral?
Yeah, actually, this is again a good question. But remember, the detection was not based on directly using any interaction that happens with the neutrino per se, because they're, as you rightly said, they're chargeless particles. Okay, but when they come and hit your detector, okay, which your detector is made of iron or sometimes made of water, made of something else, right? There is a detection material, there is an absorption material, if you like to call that as one. So any neutrinos, which let us say in our case, we are talking about solar neutrinos, which are produced, they come and then interact with the nucleons. Nucleons, I mean protons and neutrons, which are part of the iron, right? Now, depending on whether they are neutrinos or antineutrinos, when they interact, they produce either mu plus or mu minus. So antineutrinos produce mu plus and neutrinos produce mu minus. Now, and plus some other particles. Now, by applying a magnetic field to the neutrino detector, like INO, as the muons pass through, muons are produced as neutrinos interacted with, let us say, one of your protons or neutrons in the iron. And as the muons pass through, depending on the charge of the muons, because you applied an electric field, a magnetic field rather, they bend either in one direction or the other direction. Let us say mu minus is bend in this way, mu plus bend in the other way. Now, while bending, of course, depending on the bending, you will know whether it is what is the charge of this particle. And if you say this is mu minus, then you know it is neutrino. If it is mu plus, then you know it is anti-neutrino. But more than that is that since you know the magnetic field, if you can actually measure the radius of curvature of this, you will be able to estimate what is the momentum of that particle. Now, since these are relativistic particles, they travel at speed of light. So, I mean, you can say momentum and energy are something similar. So you will be able to measure the energy. You will be able to measure the energy of the particle that is produced. You are able to measure the charge of the particle that is produced. And since you know using that very sensitive TDC, whether the particle is coming from top or bottom, you will also know what is the distance that is traveled, whether it traveled 10, 20, 30 kilometers or it traveled several tens of kilometers. Okay, so that you measure and call it as L, and the energy that you measured by magnetic field, you call that as E. And then using this so-called L by E, you will be able to estimate what is the probability of an electron type neutrino going into muon type neutrino, or what is the oscillation length, like how much I can say distance before it travels, it kind of changes its flavor from one type to another type. So using these two measurements, namely the length it traveled and then the energy of the particle, you will be able to kind of study the so-called neutrino oscillation parameters, the parameters which govern a neutrino to oscillate from one type to another type. So this is how it is detected in the INO experiment. Of course, they are detected differently in different experiments. For example, in the Kamiokande experiment, which is made of water and photomultiplier tubes, so the solar neutrinos, the electron type neutrinos, come and interact with the molecules of water, producing what is called Cherenkov light. Cherenkov light is something which is a cone of light, okay? And then you will be able to kind of, using the photomultipliers, which can detect very faint light that is produced by them, you will be able to kind of measure their energies, and you will be able to also say that this is the particle which is what is the energy of this particular particle that I'm seeing. Only thing is, some of these detectors may or may not be able to have capability to track. What do you mean by track? Track means you connect up various points and then say that this particle is coming here, this particle is coming there. That's why ICAL, iron calorimeter, is a magnetized tracking calorimeter, because you are able to connect those dots and able to kind of say that this is coming from which direction and so on. So different detector techniques are used, but these are all complementary to each other. And that is how you will be able to kind of put the evidence, to do various fields, in this case, neutrino physics, but similar is the thing for any other sciences.
So the next question is, how is the IceCube Neutrino Observatory different from INO?
Yeah, it's an interesting experiment. The concept is very beautiful. IceCube, as the name says, okay, it's made of ice, natural ice that is in the South Pole. It's 1 kilometer by 1 kilometer by 1 kilometer of ice. Can you believe this? Okay, and so you don't have to spend money. It is already sitting there. Okay, of course, it's not easy. You have to go there. And what you do there is you drill through this ice some kind of bore wells. Okay, there are vertical bore wells, and through that bore well, you make like a string of photo detectors, similar in some sense, similar to what Kamiokande is doing, but you make like, it's like a string with beads, like pearls, like now there are so many pearls in one thread, for example, and many such threads you actually drop or hang through these bore wells that you already did, okay, through that 1 cubic kilometer. Now, there is something what is called threshold of energy that your detector can measure above. For example, water Cherenkov detector threshold is probably low. Iron calorimeter like ICAL is a little bit high. But when you have such a big square cubic kilometer, the thresholds are even much higher. So the ice cube experiments looks for extragalactic neutrinos which are coming not from Earth atmosphere, not from sun, far, far away, and which pass through this big gigantic detector and interact very similar way like what I told you in INO experiment. The light that is produced is picked up by these photomultipliers which are hung around all those bore wells, something very similar in some sense like a Kamiokande, except that Kamiokande has like a barrel of water and photomultipliers are all stuck over the periphery of that barrel, whereas in the case of ice cube, they're hung throughout this square kilometer area. And so as the particles that are produced when they go through these optical the digital optical modules, they're called domes, they pick up this light, and rest of the game is same. You measure what is the energy of these particles and estimate that the energies are very, very high, because that is what, see, that's what is important. The best thing is there are dozens of experiments in the world, and you cannot say that, there are so many experiments, why do you need so many of them? Each one of them look at different aspect of neutrino physics. Some of them looking at what is the mass of the neutrino, some of them look at low energy, some of them look at atmospheric neutrinos, some solar neutrinos, some extragalactic neutrino, some of them are like reactor neutrinos, and they kind of complement each other's science, and that is how the bigger game develops. So ice cube experiment, of course, there are more changes and upgrades are happening. They are also building on surface what they call ice top, another experiment. There is also another equally interesting experiments happening in Mediterranean Sea, in Europe, again below water bodies, similar to, instead of ice cube, this is below the water, okay, using sea, basically as the observer and so on. So fantastic ideas, fantastic instrumentation, detector development, electronics, IC development, great opportunities for young people.
Okay, sir. Now we have our last question. It is, what are the internship or fellowship opportunities for young engineers?
Excellent. I was waiting for this question. So as I said, quite a lot of this work that happens in any lab in any part of the world are actually done by young people. They're either done by graduate students or done by postdoctoral fellows, right? The senior people, of course, give guidance and so on and so forth. Now, in the similar vein, one could also extend this and say, I know is one big opportunity that way, where young people, especially during their summer or winter internships, can actually work and, come and work in Madurai, where most of the activities are going on. And quite few of the instrumentation that I showed you was actually built by, I think I also showed a couple of pictures, right, where the students were actually building. So one way to kind of get part of it is go through the INO web page, which is, you can Google, you will find the web page, and you also have what is called contact.us, contact.us at ino.tfr.res.in. You can apply for internships there. You can also Google on the web. You should be able to kind of find this address. Probably I should also place it. Let me type it here. I hope I'll be able to type this. ino.tfr.rs. This is the this one. I also will type the web page. Yeah, I think I typed both the web page as well as the email ID. You can actually send your CV, send your application. Usually we expect if you are a BTech or BE student, we expect in 3rd or 4th year. And if you are a science student, we expect a student to be ideally, preferably in the 2nd year, so that by the time they kind of learn. So the science students can work on some of the physics problems. The engineering students can work on some of the instrumentation and computers and electronics and so on and so forth. So that is how we run the graduate study program as well as internships.
Okay. Thank you, sir, for answering all our questions so lovingly. This brings us to the end of our event. We hope this webinar helped you learn something new today, and we express our heartfelt gratitude to Dr. B. Satyanarayana, sir, for gracing MindSpark'21 with your eminent presence.
We would also like to thank Dr. B.B. Ahuja, Director of College of Engineering Pune, Dr. M.S. Sutavne, Deputy Director of College of Engineering Pune, Dr. P.R. Dhamangaonkar, Associate Dean, Student Affairs of College of Engineering Pune, Dr. Mrs. Aarti S. Petkar, Faculty Advisor of MindSpark, for their valuable guidance.
We would also like to express our gratitude towards Digital India and AICTE for their support as patronage to MindSpark'21 and are looking forward to their continued support. I would like to thank the audience for their interest and attention. We would once again like to thank Dr. B. Satyanarayana, sir, for his esteemed presence. Thank you very much.
We
Yeah,
look
thanks
forward.
very much. Sorry, please go ahead.
Yeah. We look forward to seeing all of you in future events and experience the thrilling ride of MindSpark'21 and join us to realize the curing Mercuring vision. Thank you, sir. Thank you very much.
Yeah,
Thank you.
thanks again from my part, both to Harsh and Shruti, and also Srishti, as I also mentioned in the beginning. It's fantastic. It was a pleasure to have spent some evening with you people. I hope what I said is something of use to you, and I wish all the best for your program as well as your bright future careers. Thank you.
Thank you, sir.
Thank you, sir.
Good night.
Thank you so much, sir.
Bye-bye. Bye-bye.
Bye.
Thank you so much, sir. Thank you so much.
Bye. So can I leave?
Yes, sir.
Okay.